Binary numbers can seem intimidating at first, since they look so different from decimal numbers. But as far as the basics go, the math behind counting, adding, or subtracting binary numbers is exactly the same as with decimal numbers. It's important to call out that there aren't different kinds of numbers. Numbers are universal. There are only different notations for how to reference them. Humans, most likely because most of us have 10 fingers and 10 toes, decided on using a system with 10 individual numerals used to represent all numbers. The numerals 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9 can be combined in ways to represent any whole number in existence. Because there are 10 total numerals in use in a decimal system, another way of referring to this is as base 10. Because of the constraints of how logic gates work inside of a processor, it's way easier for computers to think of things only in terms of 0 and 1. This is also known as binary, or base 2. You can represent all whole numbers in binary in the same way you can in decimal. It just looks a little different. When you count in decimal, you move through all the numerals upward until you run out. Then you add a second column with a higher significance. Let's start counting at 0 until we get to 9. Once we get to 9, we basically just start over. We add a 1 to a new column, then start over at 0 in the original column. We repeat this process over and over in order to count all whole numbers. Counting in binary is exactly the same. It's just that you only have 2 numerals available. You start with 0, which is the same as 0 in decimal, then you increment once. Now you have 1, which is the same as 1 in decimal. Since we've already run out of numerals to use, it's time to add a new column. So now we have the number 1, 0, which is the same as 2 in decimal. 1, 1 is 3, 1, 0, 0 is 4, 1, 0, 1 is 5, 1, 1, 0 is 6, 1, 1, 1 is 7, etc. It's the exact same thing we do with decimal, just with fewer numerals at our disposal. When working with various computing technologies, you'll often run into the concept of bits, or ones and zeros. There's a pretty simple trick to figure out how many decimal numbers can be represented by a certain number of bits. If you have an 8-bit number, you can just perform the math 2 to the power of 8. This gives you 256, which lets you know that an 8-bit number can represent 256 decimal numbers. Or put another way, the numbers 0 through 255. A 4-bit number would be 2 to the power of 4, or 16 total numbers. A 16-bit number would be 2 to the power of 16, or 65,536 numbers. In order to tie this back to what you might already know, this trick doesn't only work for binary. It works for any number system. It's just the base changes. You might remember that we can also refer to binary as base 2 and decimal as base 10. All you need to do is swap out the base for what's being raised to the number of columns. For example, let's take a base 10 number with 2 columns of digits. This would translate to 10 to the power of 2. 10 to the power of 2 equals 100, which is exactly how many numbers you can represent with 2 columns of decimal digits, or the numbers 0 through 99. Similarly, 10 to the power of 3 is 1000, which is exactly how many numbers you can represent with 3 columns of decimal digits, or the numbers 0 through 999. Not only is counting in different bases the same, so is simple arithmetic like addition. In fact, binary addition is even simpler than any other base, since you only have 4 possible scenarios. 0 plus 0 equals 0, just like in decimal. 0 plus 1 equals 1, and 1 plus 0 equals 1. Should also look familiar. 1 plus 1 equals 1, 0. Looks a little different, but should still make sense. You carry a digit to the next column once you reach 10 in doing decimal addition. You carry a digit to the next column once you reach 2 when doing binary addition. Addition is what's known as an operator, and there are many operators that computers use to make calculations. 2 of the most important operators are OR and AND. In computer logic, a 1 represents true, and a 0 represents false. The way the OR operator works is you look at each digit, and if either of them is true, the result is true. The basic equation is x or y equals z, which could be read as If either x or y is true, then z is true. Otherwise, it's false. Therefore, 1 or 0 equals 1, but 0 or 0 equals 0. The operator AND does what it sounds like it does. It returns true if both values are true. Therefore, 1 and 1 equals 1, but 1 and 0 equals 0, and 0 and 0 equals 0, and so on. Now, you might be wondering why we've covered all of this. And no, it's not to confuse you. It's all really to help explain subnet masks a bit more. A subnet mask is a way for a computer to use AND operators to determine if an IP address exists on the same network. This means that the host ID portion is also known, since it'll be anything left out. Let's use the binary representation of our favorite IP address, 9.100.100.100, and our favorite subnet mask, 255.255.255.0. Once you put one on top of the other and perform a binary AND operator on each column, you'll notice that the result is the network ID and subnet ID portion of our IP address, or 9.100.100.100. The computer that just performed this operation can now compare the result with its own network ID to determine if the address is on the same network or a different one. I bet you never thought you'd have a favorite IP address or subnet, but that's what happens in the wonderful world of basic binary math.